Today we're going to be looking at real engineering, specifically NASA's plutonium problem. Look at it glow. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer, a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
We have a plutonium problem. This is Dragonfly. NASA's
Not Houston, we have a plutonium problem. Figure with NASA.
rover designed to explore Titan, the icy moon of Saturn, 1.5 billion kilometers away from Earth. And it will do it while being powered by the final few kilograms of a nuclear fuel currently left in the United States stockpile. Tucked inside this drone, nestled between thermocouples, there is a small 4.8 kilogram chunk of a man-made isotope, Plutonium-238. And the United States is running out of this vital material.
Chart is from the NRC, that's the Nuclear Regulatory Commission, and one of their jobs is accounting for radioisotopes within the US. And yeah, well, there was less demand than there was during the Cold War, as Plutonium-238 was generated in specialized reactors designed to aid in producing weapons. So Plutonium-238 is not produced as a byproduct of commercial nuclear power plants. Now there you get Plutonium-239. And the reason for that is the typical reaction is with a uranium-238, which is the majority of the nuclear fuel by mass percentage, not by ability to cause fissions, that's uranium-235, but by mass percentage. So uranium-238 gets bombarded with a neutron, becomes uranium-239, 2 beta decays later, you get plutonium-239, which is also fissile. So it gets used as fuel. Toward the end of a fuel cycle, you're actually burning plutonium. But you don't get much 238, but you don't get 238 you don't get plutonium-238 over the course of a typical nuclear fuel cycle.
Shortage has already affected NASA missions, like the Europa Clipper's mission to Jupiter's moon, where it will need to get by with the power provided to it with its solar panels, which will receive extremely low intensity light in the distant reaches of our solar system.
Yet another advantage that nuclear has over solar, because solar follows the inverse square law, in that you double your distance from the sun, intensity is going to drop off by a factor of 4. So talking about solar power on Mars and areas beyond Mars, it's not going to be very much. Going to be much better off with nuclear power. My 100% biased opinion.
Many at JPL believed Europa Clipper should have been powered by Plutonium-238, but with the material in short supply, it was saved for missions like Dragonfly. This isn't good. It's quite bad, actually. We really need more plutonium.
I love that. This isn't good, it's quite bad.
38 to do cool science stuff. So, what are we going to do about it?
Make more. Get those specialized reactors up and running in places like Oak Ridge National Lab. And just like with turning uranium-238 into plutonium-239, your precursor is going to be neptunium-237. Going to turn that into plutonium-238 by placing it in a neutron field in a reactor.
This hasn't always been a problem. Some positive things did come out of the world's relentless race to expand nuclear weapon arsenals during the Cold War. Like this, and even this. Deep within secretive...
What was that? I'm gonna have to back up. Wow, really? I don't even know what to say.
Deep within secretive processing facilities around the world in the 1950s, scientists began producing fissile plutonium-239 in vast quantities. The United States, Russia, United Kingdom...
I think you meant to say, and plutonium-239 is good for making your weapons because it's way more reactive in the fission stage of your weapons than your uranium-235, about 3 times more reactive. Now, I did say it is used in civilian nuclear power plants. No, it's not going to make your reactor produce 3 times more power. That is all going to be driven carefully by the reactor's control systems to maintain 100% power. What it does mean for reactor operations is the reactor responds a little faster. Because for one, it's not all plutonium-239. At most, you're getting to 20-30%, depending on reactor design, as far as your active ingredient of plutonium-239 versus uranium-235. But it, like I said, it just makes your reactor respond faster. And it is good to produce it because it extends your fuel life a little bit. You're getting a bit more fuel efficiency out of your reactor.
France, China, and Israel all developed nuclear weapons during this time. And in the process of refining and extracting weapons-grade plutonium, other isotopes emerged, useless for warheads and discarded as waste. Or so it seemed. NASA saw something different. What the military considered a byproduct, they saw as an opportunity. Among the leftovers were the ingredients to make plutonium-238, an isotope unlike its bomb-making counterpart.
That's a cool little animation he's got. He actually put 238 of them in there.
It doesn't sustain a chain reaction, but instead, it emits a steady, reliable heat. This isotope could be harnessed as a safe lifeline for spacecraft venturing into the darkest, coldest corners of the solar system.
So advantages of plutonium-238 is it's safe. It's mainly an alpha emitter, so your shielding requirements is less, and your energy packet is more dense, which makes this an ideal choice to generate heat, because it's all going to be localized in close range, compared to something that's going to radiate gammas that are just going to penetrate and be less useful in interacting with the thermoelectric materials. It has a pretty long half-life, 87 years compared to something like cesium-137 or strontium-90, which only have a half-life of 30 years. Now, those are more common fission products, though, so you're going to get more of that, but those aren't as good. Also, they are going to emit betas and gammas, which are more penetrative and less useful for essentially making a nuclear engine out of this. And as mentioned earlier, this is great in areas of little to no sunlight, so you venture far away, you venture to Mars and beyond, solar power is going to be way less effective as an alternative. It has high power density as well. Its energy output per gram is significantly higher than other isotopes as well.
The only way to create this element is to bombard other elements with neutrons in a nuclear reactor. This isotope is differentiated from the one that leveled Nagasaki by just a single neutron. This single neutron difference changes plutonium from one of the most tightly controlled substances in the world to this.
It's still going to be tightly controlled. Notice the graph he used earlier was from the Nuclear Regulatory Commission, but I get what he's saying. 238 isn't like 239 in terms of sustaining a fission reaction. Though, technically it could sustain a fission reaction, but it's so good as an RTG source, it produces so much heat from its decay that good luck making a warhead out of it.
Full material glows red hot, not for hours, not for days, not for weeks or months or years, but decades.
Sure.
A slow,
87.
consistent radiation of heat that halves every 88 years. And this heat can be used to generate electricity, but more on that later.
So a good rule of thumb about half-lives, there's a few misconceptions out there. Like, one is 2 half-lives, it's gone. No. As that graph showed, it's an exponential decay function. Meaning, after 2 half-lives, you're down to about 25% of your source material. Depending on how conservative you are, 8 to 10 half-lives is when you say it's basically gone. So that half-life could translate to century-plus long missions where you just need sustained low power output, but sustained, such as space probes, or remote Arctic instrumentation that you don't want to send somebody out there to replace a battery or anything like that.
Since its discovery as a power source, plutonium-238 has been vital to NASA's missions. First used in the Apollo lunar surface experiments, it later powered the Voyager probes, which are still transmitting from interstellar space. Cassini explored Saturn with its help. The Curiosity and Perseverance rovers roamed Mars with its heat. And now, Dragonfly will rely on it to explore Saturn's moon, Titan, keeping its instruments running in the extreme cold and providing the energy needed for powered flight on another planet's moon. So, why are we running out of this wonderful material? In 1988, with aging reactors and a nuclear weapons stockpile so large they could end the world instantly, the United States...
No, that's that's a whole separate topic for another video, but end the world instantly. I guess you can argue that in terms of like disrupting the world economy, sure, but if you're talking about ending all life on Earth, no, that not even close.
Halted its production of weapons-grade plutonium. I think we can all agree this was a good thing, but this decision has hindered deep space exploration. With the shutting down of the K reactor in the Savannah River site, the US lost its ability to produce plutonium-238.
This is another challenge when something has been shut down for a while. There's just going to be a generation gap, knowledge gap. I would say less extreme because you don't need as much infrastructure to, say, building a whole fleet of commercial nuclear power plants, but it's still significant.
Forcing NASA to ration a dwindling supply of the valuable material. This problem became even worse when in 2010, the US stopped importing the isotope from Russia. So, a decade ago, NASA and the Department of Energy,
not something that you really want to be dependent on,
restarted its complex production. But with current production at just 550 grams per year, supply is not keeping pace with demand. So, what is NASA doing to address this problem?
So one of the challenges, and why you can't just, say, stick some Neptunium-237 in a commercial nuclear power plant and go to town, is you need reactors with a high enough neutron flux. And commercial reactors, you also don't want something to compete with your uranium-235 in terms of causing fissions and producing electricity. So you're going to want a specialized production type reactor as opposed to a power generation type reactor. And a lot of them also have other regulatory and government and security clearance type requirements. One example of such a facility is the high flux isotope reactor at Oak Ridge National Lab that's designed to make plutonium-238. So there's your production bottleneck, is needing more of those. And I already mentioned the knowledge transfer, because we haven't done this as much in a while. Not as many people are experts in this specific process.
There are some alternatives if plutonium refining does not increase to meet demand. The first thermal generator tested by NASA in 1959 used polonium-210 as its nuclear source.
That stuff is way more toxic. I mean, for a drone-operated space probe, you can argue that's less of a concern, but it also has a really short half-life on the order of 140 days.
A single gram of polonium-210 generates 140 watts of power. However, its short half-life means its power output halves in just 138 days. The fastest ever journey to Mars,
you might as well just use regular batteries at that point.
About the same time. During that time, the spacecraft would have to radiate that heat generated by the fuel to space. Losing half your power before you've even arrived isn't ideal, ruling it out of most space missions. The unique demands of space exploration gave rise to 3 primary engineering requirements for a nuclear fuel suitable for spacecraft. The first requirement is that the fuel must last long enough to power a mission without sacrificing energy density. This means the isotope's half-life should be between 15 and 100 years. Out of nearly 2,900 radioisotopes,
15 years would be pretty close to 100% power.
Criterion reduces the options to just 22. Next, the fuel must only emit radiation that is easy to shield, ensuring the protection of both the spacecraft's sensitive instruments and any personnel handling it during preparation.
So here's your classic diagram of showing what's effective at stopping. One misconception about this is it's showing paper completely stopping alpha particles. That's not completely true. I believe Thought Emporium has made some videos using a particle detector to show that, alphas are getting through, but it stops a lot of them. So the point is still 100% valid that alpha particles are a lot easier to block. And as far as the dose hazard, mainly don't eat your alpha source. So please don't eat your plutonium-238 or any other radioisotope for that matter. Now, one thing is gammas can actually penetrate a little bit of concrete, but most concrete is fairly thick enough. It's mainly things that are ultra dense, such as lead or tungsten or even uranium and plutonium, oddly enough. But concrete is mainly used to shield against neutrons. Now, thick enough anything, you can stop gammas. So you have thick enough concrete, yeah, it's going to stop your gammas. But ultimately, this is just showing that gammas are far more penetrative than betas or alphas.
This means of alpha, beta, and gamma particles, we want the material to only emit alpha particles, which generate more heat and are easily blocked.
And that's the other key thing, is they generate more heat, because ultimately you want the thing to provide heat to make your electricity.
The alpha particles emitted by plutonium-238 are essentially helium nuclei traveling at 15% the speed of light and carrying 5 mega electron volts of energy. As they
never seen it abbreviated mega-EV. That makes it sound like some kind of robot. That's cool.
With electrons and nuclei within the fuel, they release their energy as heat. But if emitted near the pellet's edge, the alpha particles are easily stopped by light materials. But it's not the only alpha emitter. Take Curium-244. Its half-life, 18 years, is a little short, but...
Note the word spontaneous fission. Yes, you don't always need neutrons to fission. That means it decays by sloughing off a chunk of nucleus that is bigger than an alpha particle. Alphas are a lot more common just because they're very stable. But spontaneous fission, we're not talking like it's gonna start a self-sustaining fission reaction. It just means it's gonna decay some bigger, even shorter range, and even higher energy density source. But it's considerably less common. Curium-244 is mainly known as an alpha source. Technically, something like uranium-238 has a spontaneous fission half-life, which is far longer than its alpha half-life. Considering its alpha half-life is 5 billion years, you're not going to see many spontaneous fissions.
Within the acceptable range. Curium-244 was initially considered as a potential substitute due to its high power density, which is 5 times greater than that of plutonium-238, and it has a stable high-temperature oxide fuel form. But its higher gamma and neutron emissions, resulting from its higher rate of spontaneous fission, significantly increases the need for heavy shielding to protect both handlers and spacecraft equipment. Plus,
there's just a lot more going on with it.
Producing Curium-244 is far more difficult. The best way to create it is for plutonium-239 to capture successive neutrons and for it to decay into curium.
That successive neutrons is a lot more challenging. Each step is potentially a lot of work, and each of these individual steps, it's not certain to happen. When plutonium-239 interacts with a neutron, for instance, it could fission. So the fission, it's all competing resources here. There's a chance it could fission, there's a chance it could absorb the neutron, there's a chance it could scatter the neutron and not even do anything with it. And that's assuming the neutron hits or gets close enough to it. The neutron could just miss completely. So you got these calculations for everything. Plutonium-240 is not likely to fission, but 241 could. One general rule of thumb is when looking at these isotopes of plutonium and uranium, the odd-numbered ones are more likely to fission than the even-numbered ones. The even-numbered ones would require very specific conditions, such as fast neutrons. That's not 100% true, but it's a good rule of thumb to keep in the back of your mind.
It is expensive and impractical, so there is currently no infrastructure to produce it in the large quantities needed for space missions.
Yeah.
Stability under extreme conditions is equally critical. The fuel has to withstand launch accidents and atmospheric re-entry. We don't use completely pure plutonium-238 in spacecraft. Instead, they rely on plutonium oxide pellets, which are encased in iridium shells to contain the material safely.
That's the same case with, you don't use pure uranium-235 in nuclear power plants. In fact, very little of it is uranium-235. We're talking 2 to 5% enriched, depending on design. But even still, it's uranium oxide pellets. And it is also clad, like there's cladding. It's mentioning thermal insulator sleeves and shells. So yeah, we're not just taking hunks of 240 and just having it sit there exposed.
Iridium was chosen because of its high temperature material properties, being strong and ductile even at 1000 degrees Celsius, allowing it to safely deform and contain the radioactive pellets in the event of an accident. In 1967, a plutonium generator was recovered from the Pacific Ocean after a failed launch of a weather satellite. its plutonium-238 was reprocessed and successfully used in another mission. Similarly, during the Apollo 13 mission, the lunar module's generator sank intact to the ocean floor, where it remains safely contained, keeping some local fish warm. Finally,
generally underwater is a pretty good spot for any radioisotope. It's, for all intents and purposes, the size difference, it's a near infinite heat sink for you. It's also really good at absorbing radiation as well.
Fuel must be cost-effective and producible in sufficient quantities, using existing infrastructure like nuclear reactors. Gadolinium-148 is another great option, with a long half-life of 75 years with only alpha decay mechanisms. But the only way to produce it is to bombard targets with very high energy protons, requiring very expensive particle accelerators. So
it's not a common fission product, so good luck extracting that from a reactor.
To produce it in enough quantities, a much larger investment is needed. So, in short, plutonium-238 is just a miracle material that is perfect for space exploration. NASA has two options to tackle this supply and demand imbalance: either increase production or figure out a way to use current supplies more effectively.
Or import, but I think we touched upon that one already.
The current method of extracting electricity relies on the Seebeck effect. The Seebeck effect is
how a thermocouple works, basically.
Allows us to generate an electric current through a heat differential. As charge carriers, both electrons and electron holes will move from hot to cold. So, if we have two semiconductors, one with charge carriers in the form of electrons and one with charge carriers in the form of holes, a potential difference between the two semiconductors will form when a heat gradient is applied. This potential difference causes a current to flow in the external circuit.
And we're not talking massive orders of magnitude, we're talking on the order of watts, but for very long time periods.
Conductors need to be both thermally insulating to ensure this heat gradient is maximized, but also electrically conductive to maximize the current. These two material properties are typically linked. Copper is both a great electric and heat conductor, while iron is a poor electric and heat conductor. Having a single material that is a great electric conductor and a poor heat conductor is extremely rare. For this reason, two unique materials are used for the P and N-type semiconductors: lead telluride for the N-type and an alloy commonly called tags for the P-type, which is formed from tellurium, silver, germanium, and antimony. NASA has explored more efficient ways to generate electricity with the heat plutonium-238 provides, including the use of the Stirling cycle. This cycle operates by alternating compressing and expanding a gas in a sealed system, allowing heat to be converted into mechanical energy, which then drives a generator to produce electricity.
I like all the explanations here. They're very simple and high level, and it really shows all the different, mechanical materials integration in addition to the nuclear stuff.
NASA focused its efforts on developing an advanced Stirling engine, a highly efficient system designed to work in the vacuum of space and be able to survive the harsh vibrational forces of the launch. Traditional radioisotope thermoelectric generators only convert heat to electricity at an efficiency of only 6 to 7%. Stirling engines can achieve efficiencies of up to 30%. This would more than quarter the quantity of plutonium needed for these space missions. Unfortunately, in 2013, after a decade of development, NASA cancelled the Advanced Stirling Radioisotope Generator project due to technical issues with the piston, underestimated costs and schedules, and budget constraints.
I mean, that's always the trade-off with newer technology, and it's kind of, is it worth the trade-off, or is it you're better off just making more plutonium-238?
So, increasing production is the only option left. Production restarted in 2015, and while initial production was just 50 grams per year, to date, the production level is 550 grams, with plans to raise that to 1.5 kilograms per year.
Demand goes up, makes sense.
Current production entails 3 different facilities in 3 different states. During the Cold War, the Savannah River site separated and produced 400 kilograms of neptunium. Its long half-life means it's still usable as a target even to this day. All of the plutonium in the future lunar landers and the Dragonfly mission will be made from neptunium made decades ago, stored in a site in Indiana.
That's one step
The
out of the way.
neptunium, as a solution, gets transferred to the Oak Ridge National Laboratory. There, they distill the solution and precipitate the neptunium to create a metallic powder. This
That's
material
cool.
is then carefully pressed into pellets.
I like the little green light on there. It just has nothing to do with neptunium. It's just that it's just funny to see that they're using green glowy stuff.
Encapsulated in aluminium to prepare it for irradiation. The encapsulation ensures that neptunium remains contained during its transformation in the reactor, maintaining safety and preventing contamination. Next, the encapsulated neptunium is placed inside a nuclear reactor, where it undergoes irradiation. Inside the reactor, the neptunium-237
with
nuclei
neutrons.
absorbs neutrons to form neptunium-238. This isotope is highly unstable and quickly decays into plutonium-238 through beta decay. The reactor's neutron flux and duration of irradiation are carefully controlled to optimize the conversion rate and ensure the production of high-quality plutonium-238.
And again, as far as to why you need these specialized facilities, you get a bit of neptunium-237 as a byproduct, but it's not worth the specialized extraction you would need to do from, say, nuclear waste products. So while it is an expensive process involving the use of a nuclear reactor, a very specialized nuclear reactor, chemical separation techniques, and various types of radiation shielding depending on what stage you are in the synthesis of this, it can be difficult to justify unless there's this massive urge to do a whole lot of space missions that involve plutonium-238. But if that demand continues to go up, that'll be a reason to produce more of the stuff. Get enough. If we're going to use 1.5 kilograms a year, then production will eventually have to go up, or priorities will just simply have to shift.
Radiation. The targets containing plutonium-238 are removed from the reactor and processed to extract the newly formed plutonium. This involves dissolving the irradiated material in acid and using chemical techniques to separate plutonium-238 from any residual neptunium-237 and other byproducts.
You don't see that much, even in the terms of on the waste management side of commercial nuclear power, to dissolve things in acid and powdering it out. Yeah, it's just not as... This is a very specific thing that would require different training, even if you move people over from, say, commercial nuclear power plants. There's some different operational skills at work here. A lot more chemistry, or not more chemistry, just different types of chemistry than you would for maintaining a nuclear power plant.
Extracted plutonium-238 is then purified further to meet the rigorous standards required for use in space missions. Finally, it's converted into a ceramic oxide form, which is stable and suitable for use in radioisotope power systems, and sent to the Los Alamos lab in New Mexico to be formed into the final pellets and placed inside the thermal generator. In 2011, when the Department of Energy started up the process, none of these facilities were ready for large-scale operation. They needed $90 million for modifications to existing facilities. All of this is simple in theory, and the overall process...
I was going to say that control room looked more modern because it had a whole bunch of touchscreens in there.
has been known since the Cold War, so why has it been so hard to build up the stockpile? Engineers and researchers are fighting a losing battle against unstable elements that are impossible to see. It's easy to write the diagram where neptunium simply turns into the right kind of plutonium by absorbing a neutron. But in reality, this is a statistical process. In the hot, messy, and energetic environment of the target.
Anything involving nuclear reactions, whether it be fissions, whether it be decay, whether it be a series of neutron absorptions like what you're seeing here, is a Monte Carlo simulation. And the term cross-section is used, or the term barn is used, to describe the probability of these absorption reactions occurring. It's also used to measure probability for fission. But the unit for a barn is 10 to the minus 28 square meters. And it comes from the expression that you can't hit the broadside of a barn. These barns are really small and pretty hard to hit.
Anything can happen. Neptunium might absorb one neutron and then split. Ideally, it absorbs a neutron and becomes Neptunium-238.
I'm glad he's
Once
covering this
formed,
part.
this Neptunium is also exposed to the same neutron bombardment. This is actually the main way Neptunium-238 decays. 85% of the Neptunium-238 that is created is destroyed by neutron-triggered fission. Then, in the off chance that everything goes,
especially since we're dealing with high flux and higher chances of interactions with fast neutrons,
and the Plutonium-238 starts to build up in the target, it is still being irradiated too, creating even more undesired isotopes. We need 85% pure Plutonium-238 and trying to separate two isotopes that differ in mass by 1.
Enriching stuff into that higher concentrations is very challenging to do. It's doable. That's why you need facilities with massive amounts of centrifuges to make weapons grade plutonium, which is this guy on the right, 239.
Or 2 neutrons is almost impossible. These interactions are incredibly difficult to control. During one cycle, 1 gram of neptunium would yield just 0.5 grams of plutonium. To maximize the likelihood of plutonium-238 forming, we want to expose the target to a stream of very concentrated neutrons for a short time in cycles.
And also, concentration, neutrons at a specific energy level to help increase this probability, because not all neutrons are created equally. It's a various spectrum of neutron energies designed to increase the chance of this happening. It's a lot more precise than trying to cause fissions in a power plant. That you're not looking, there's no specific timing of when to essentially turn the neutron reactions on. There you're dealing with a self-sustaining reaction, and that's what makes that easy operationally.
In the cycles, the target is allowed to cool, while unwanted byproducts decay further. There are very few facilities capable of doing this, just 2. The high-flux isotope reactor at the Oak Ridge National Laboratory and the Advanced Test Reactor at the Idaho National Laboratory. And there is huge demand for these reactors. Nuclear physicists depend on these slots being available to study different isotopes. So the lack of places to irradiate the targets in addition to the low yield means the number game is not in our favor to build up the stockpile. So where do we go from here? The production process is slow and complex. The Oak Ridge National Laboratory is on track to produce 1.5 kilograms of plutonium-238 per year. The Dragonfly mission alone will need around 4.8 kilograms, taking 3 years to produce. So we desperately need to increase supply because there are many more exciting missions that could use this incredible material if it was available. The success of the restart of US plutonium production has sparked interest in other space organizations. The ESA is well positioned to create their own manufacturing plant. France, having a large nuclear power base already, has a full facility meant to extract plutonium and uranium from spent nuclear fuels in La Hague. Looking to the near future, the possibility of using plutonium-238 for lunar missions is gaining attention. While the moon offers better conditions for solar power compared to deep space, certain lunar regions, such as permanently shadowed craters at the poles, require...
the moon's basically tidally locked, so it's only good for half the moon. Actually, less than half.
...power sources. These regions are of high scientific interest, as they may contain water ice and other valuable resources.
Yeah, like helium-3 for fusion, so we're using fission reactors to create materials using the neutron absorption process to extract materials that could potentially be used for a different nuclear process in fusion. A lot of opportunities for nuclear, in case you're wondering.
A steady plutonium-238 supply could enable extended exploration of these areas, powering landers, rovers, and even infrastructure like communication relays or habitat systems during the long lunar nights. Ultimately, there is only one answer to this problem. Scaling up plutonium-238 production to support both lunar and deep space missions is going to require a lot of money.
So does everything else. But if we get better at making this stuff, the cost should come down. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.